Okay, so in this video I want to go over something called the Schmidt process. This is a way to take a set of vectors, v1 through vm, that are linearly independent, and then convert that, it's an algorithm that will take these set of vectors and return an orthonormal set of vectors that has the spans the same space. So they're gonna be bases for the same thing. So you take a basis for one set, for one space, the Schmidt process will return an orthonormal set. An orthonormal basis for that same set, and in the video that I made before, that explains why we want there to be an orthonormal set. Okay, so here's what's going to happen. I'm going to describe the algorithm over here, and then I'll give the algorithm more generically. Okay, so we're going to look our first vector. We're going to call it q1 hat. There's going to be a general pattern. q1 hat is just going to be equal to v1. And then we're going to say that q1 is just going to be equal to q1 hat divided by the norm of q1 hat. Okay, so all we're doing here, all this is doing, our vectors that the algorithm returns are going to be the q vectors. This is just saying the first vector is just going to be v1 divided by its magnitude. So just the unit normalized version of v1. Okay, now what's going to happen next is let me do it over here actually, because I'm gonna write the algorithm over here when I have explained it. q2 hat. What we're going to do is at each step, okay, we're going to take q2 hat and we're going to subtract from v2. We're going to subtract off the projection onto q1. And then when we get to q2 hat, and we're going to do something to get a q1 vector. And then q3 hat, we're going to take v3 and subtract off its projection onto the space spanned by q1 and q2, and we're going to continue in this manner. So q2 hat is going to be equal to v2 minus the projection of v2 onto q1. And for reasons that I said in the previous video, q2 hat is going to be orthogonal to q1, because we're taking v2 and we are removing from v2 the part of v2 that is parallel to q1, and so all that we're left with is the part of v2 that is perpendicular to q1. So q2 hat is going to be orthogonal to q1. Okay, the same argument that I gave before and the video before shows that this is true. So something that you should do to verify for yourself. Okay, and then we're going to say that q2 is just going to be equal to q2 hat divided by its magnitude. Okay, and we're doing that step just because we want them not to merely be orthogonal, but to be orthonormal. Okay. And then let me show you what q3 is going to be, and you'll probably be able to pick up the pattern. So q3, we're going to take v3 and subtract off the projection of v3 onto the space spanned by q1 and q2. And so this is going to be minus the projection of v3 onto q1 and the projection of v3 on to q2 like this. Okay, so again, because we are from v3 subtracting off the portion of v3 that is in the space spanned by q1 and q2, all we're left with is the part of v3 that is orthogonal to the space spanned by q1 and q2. So therefore q3 hat is going to be orthogonal to q1 and q2. Okay, and then as you might expect, q3 is simply going to be q3 hat divided by its magnitude. Okay, so now maybe we can see in general what's going to happen. I'm going to kneel just so you can see the board and so I can write clearly. In general, qk hat is going to be equal to not v3 but vk minus the sum j equals 1 to k minus 1, and we're going to do the projection of vk onto qj like this. Not qj hat, but qj like that. Okay, and then what we're going to say then is qk is going to be equal to qk hat divided by its magnitude. Okay, so that's what qk is. Okay, and again, like I said, I want you to actually go through the computation and show that qk hat is orthogonal to q1, q2, all the way up to qk minus 1. It's going to be the same exact, well, it's going to be very similar to the argument I mentioned in the previous video, but then I said, show in general that the projection formulas I gave you are going to give you a vector. That's, when you look at the previous video, and I showed you, I basically showed how to show that qk hat is orthogonal to the ones that come before it. Okay, so take some time to do that. Because I'm not going to do it here for you, I want you to think about it. Okay, so in general, I'm going to kind of write the algorithm over here in the way that's more how we're going to think about it. So there's sort of an initialization step. So there's going to be a loop, but there's a first initialization step. The first initialization step is we're going to say that qk hat, q1 hat is equal to v1, r11 is equal to the magnitude of q1 hat, and then q1 is going to be equal to q1 hat divided by r11. Okay, now in the main loop, we're going to have a couple of different things. So for k equals 2 to m, we're going to do the following. So 1, I need to make sure that I get this right. R j k is equal to the inner product of vk and qj. So I've made this video before. This is the second time I made the video. The first time I had rkj instead of rjk, and it's not a huge deal, but it messed everything else up. So I wanted to make sure that I didn't make that mistake this time. Okay, and then we're going to say that qk hat is equal to vk minus the sum j equals 1 to k minus 1 r jk times qj. Okay, and then 2 r kk is equal to the magnitude of qk hat, and as you probably guessed, qk is going to be equal to qk hat divided by r kk. Anytime we're dividing, we have to worry about whether or not this can be 0. As long as the vectors v1 through vm are linearly independent, this is never going to be equal to 0. Okay. So here's what I want to show now. Here's what I want to show now. Notice what I have here. If I look at this right here, if I rearrange things, then I can write V as a linear combination of the Q's. And this is going to be something that's important. So I'm going to set notation here, and I want the matrix V to be the matrix whose columns are given by these vectors here. And what this algorithm is going to let us do, in addition to having an orthogonal set of vectors like this, what it's going to let us do is decompose this matrix in a special way. We're going to decompose it according to something called the QR factorization, and I'm going to show you what that is now. Okay, so notice that if I look at this equation right here, I can solve this for VK. And I've got that VK is going to be equal to the sum j equals 1 to m r jk q j plus qk hat. But what is qk hat? Qk hat is simply qk times rkk. This is j equals 1 to k minus 1. Qk hat is qk times rkk. But notice what happens here. If j is equal to k, I know the sum only goes up to k minus 1, but if j is equal to k, this is rkk qk. So this is exactly the kth term of this sum. In other words, I can just write it like this. But now what do I have here? I have a linear combination of vectors. And I can always write a linear combination of vectors as matrix vector multiplication. So I can write this in the following way. Matrix whose first column is q, whose second column is q2, all the way up, whose last column is going to be qk, and then times, k is going to be the one that's fixed, and j is the one that's changing. So we're going to have r1k, r2k, all the way down to rkk. Now this is certainly true, but I want a matrix here that does not depend on k. So here's what I'm going to do. I'm going to expand this matrix. I'm going to have q1. I'm going to have q2. I'm going to go all the way down to qk. But then I'm also going to go all the way down to qm. Okay, so like after I've done the Schmidt process, I have all of these vectors. So I'm going to make this. Now this matrix has m columns. So whatever vector I have here needs to have m entries. Well, all of the vectors that come after that are not part of this linear combination. So I'm just going to basically pad this vector with zeros. And so I'm going to have r1k, r2k, down to rkk, and then all of these are going to be 0. Okay, so these are now going to be equal to each other. Okay, so this matrix right here is called Q. We're going to call it Q, and it doesn't depend on K now. It's just the Q does not depend on K. It is just the matrix whose columns are given by the vectors that are returned in the Schmidt process. So then we can write this as Q, and then times the vector r1k down to rkk, and zeros everywhere else. Well, now for every, this is vk, so for every k, I'm going to have one of these different vectors. But notice, this says that the kth column of v is equal to q times this vector right here. So then I can say v is going to be equal to q times a certain matrix. What is the matrix? Well, for k equals 1, it's just going to be r1, 1, and zeros everywhere else. So q, remember when we do the definition of matrix multiplication, the first column of v is going to be q times the first column of this matrix. So v2, which is the second column of the matrix v, is going to be q times the second column of this matrix here. So this is going to be r1, 2, r2, 2, 0, all the way down like that. And so the third column is going, the v3 is the third column of v, is going to be q times the third column of this matrix. So we're going to have r1, 3, r2, 3, r3, 3, and then zeros all the way down. And then finally, the last column is going to be r1, R1M, R2M, and then finally down here to RMM. Okay, and this matrix is called R. This matrix is called R. Now let's just do a little sanity check. What are the dimensions of Q? Okay, well, the columns of Q are these vectors, little q. So there are n entries in each one of those. So there are n rows in big Q. And there are m of them. So Q is an n by m matrix. Okay, what about R? Well, this tells us that the bottom right entry has indices mm. So then R is an m by m matrix. So m by m, or m and m, those are equal. So this tells us this product is well defined. And then the dimensions are going to be n by m. And this is an n by m, V here is an n by m matrix because all of these vectors are in n-dimensional space. And so they have n entries in them. So there are n rows and there are m of them. So there are m columns. And so this is exactly, what it should be. Okay. So this is the Gram-Schmidt process, and then this right here is called the QR factorization of the matrix V. One thing to point out, if we look at Q, Q and R have special properties. If we do Q transpose times Q, do true Q transpose times Q, what are we going to get? Well, let's remember that Q is an n by m matrix, so Q transpose is going to be an m by n matrix. When we do this, we're going to get the identity matrix, the m by m identity matrix. And I want you to think about why that is. It's because the columns of Q are orthonormal. Okay, they're orthogonal, so that means there's going to be zeros everywhere except for the diagonal. And since they have unit magnitude or unit norm, the diagonals are all going to be 1. I want you to prove this. I want you to make sure you understand why this is true. Okay, and if you, again, feel free to ask if you want to know why. The other thing is that R is upper triangular. Meaning it has the form like this, where we've got stuff on the diagonal and everything below it is 0, and that's just whatever it happens to be. There might be some 0 entries up there, but we're going to have all zeros down here below the diagonal. So it's upper triangular. So this is a very nice way to factor V. Both of these matrices, Q and R, are easier to deal with than both of the matrices Q and R are easier to deal with in certain circumstances than the matrix V. And so sometimes it's worthwhile doing this maybe computationally intensive Gram-Schmidt process to be able to get the QR factorization for the matrix. And these are the sorts of things that we're going to talk about in this class. One of the things we're going to talk about in this class. It's not going to be, well, okay, you'll see how big of a point it is. Now, this is all pretty abstract, and so the last thing that I want to do is I just want to do an example. Whoa, that was weird. Now I'm wearing a different shirt. Okay, so I was going to do an example, but I started doing the example yesterday, realized I had not left myself enough room to be able to show everything like I needed to show, and it just wasn't going very well. So here I am. I'm going to do a different, it's another day. I had to go home to do some things. And so now I'm going to do the example of the Gram-Schmidt process, and as a part of that, compute the QR factorization of this matrix here. So there's sort of two things, two different ways we can view this. I've got these three vectors, V1, V2, V3. Maybe I'll just label this as this first column is V1, this second column is V2, and the third column is V3. So I'm going to show you the Gram-Schmidt process to get an orthonormal set of vectors that has the same span as these three vectors. And remember, we saw in the previous video, as a byproduct of that, we can sort of compute the QR factorization of the matrix. And so that's what I'm going to do now. So I'm going to do my work over here. And then this will be the Q matrix, which will record the orthonormal basis vectors we get from that. And this will be the R matrix, which will encode the inner products as I have listed them here. Now there's a 0th step, sort of an initialization step, the k equals 1 step that I had to erase to fit the matrix, but I will remind you Q1 hat is just equal to V1, which in this case is 1, 1, 0, 0, 0, and then R11 is the magnitude of this vector. Well, the magnitude of that vector is the square root of 2. And so then Q1 is just going to be this vector divided by its magnitude. So it's going to be 1 over the square root of 2, 1, 1, 0, 0, 0. Okay, so this is the Q matrix. The first column of this matrix is going to be that vector, that Q1 vector. So we're going to have 1 over the square root of 2, 1 over the square root of 2, and all of the bottom three entries are 0. Okay, so what we have here, just to go back a little bit, these three vectors, V1, V2, and V3, I will let you show for yourself that they are linearly independent. One way you could do that is row reduce this matrix, and you'll see that each column has a pivot, and therefore that's one of the things in linear algebra that you learn is equivalent to the vectors being linearly independent. Or show it a different way, but these three vectors are linearly independent, okay? And so now we're going to get an orthonormal basis Q1, Q2, and Q3 that spans the same subspace. So these vectors are in R5, they span a three-dimensional subset of R3. And so we're going to get an orthonormal basis for that subset. Okay, so this is what Q1 is. And then remember, the thing that goes here is R11, which is square root of 2. And now we're going to get 0, 0 here. Okay. Okay. All right, so now let's move on to Q2. So we're going to use this algorithm here. We're going to use this outline here. So we're first going to compute RJK. So so k is equal to 2 now. This should say 2. So k is equal to 2. And we're going to compute these RJKs. So R1, 2. Actually, let me write it out in a way that will sort of be a little more clear, I think. So Q2 hat is going to be equal to V2, which is this vector right here. 1, 0, 1, 0, 0. And then we're going to subtract off the projection of V2 onto Q1. Okay, so we're going to do the dot product of V2 and Q1. And so what are we going to get when we do that? We're going to have 1 times 1 over the square root of 2 plus 0 times 1 over the square root of 2 plus 1 times 0 plus 0 times 0 plus 0 times 0. And so the dot product of V2 with Q1 is just going to be 1 over the square root of 2. So we're going to have 1 over the square root of 2, and that's going to be R12. And now we're going to multiply it by Q1, which is this, which is 1 over the square root of 2, 1 over the square root of 2, 0, 0, 0. Okay, now what do we get here? Okay, well the square roots, there's a square root on the outside and a square root on the inside. So I'm just going to sort of do this multiplication in place, but when we do 1 over the square root of 2 times 1 over the square root of 2, we just get 1/2 on the inside. So this is, R12 is 1 over the square root of 2. So let me record that here, 1 over the square root of 2. And then we're going to get 1/2, 1/2, 0, 0, 0. Yes, okay. Okay, now I'm going to do this subtraction, 1/2 minus 1/2 is 1/2. 0 minus a half is minus a half. 1 minus 0, so they're not lined up exactly right. 1 minus 0 is 1, and the bottom entries are going to be equal to 0. Okay, so this is Q2 hat. Okay, that's Q2 hat. All right, so now we need to compute R22, which is the norm of this vector. R22, which is the norm of this vector. One way to do this that might make things a little bit simple, if we pull out a 1/2, we're going to get a 1 here, and then this will have to be a 2. Look, however you guys want to compute the magnitude of this vector is fine with me, but I'm going to use the fact that R12 is going to be equal to 1/2 of the magnitude of this vector. The magnitude of this vector is the square root of 2 squared, 4, plus 1, plus 1. So 4, 5, 6, the square root of 6. So 1/2 times the square root of 6. Okay, the square root of 6 is of course 3 times 2. So the square root of 6 is the square root of 3 times the square root of 2. And so this is going to be equal to the square root of 2, the square root of 3 divided by the square root of 2, because the square root of 2 divided by 2 is just 1 over the square root of 2. Okay, so we're going to have square root of 3 divided by the square root of 2, and then a 0 here. Okay, and then this, if we divide this, so we need to divide this vector by R22. Okay, so what that means is we're going to multiply it by the reciprocal. Okay, so now what we're going to get, when we multiply it by the reciprocal, the square root of 2 divided by 2 is 1 over the square root of 2. And so it's going to be 1. Again, we're going to, when we multiply this by the square root of 2, it's going to be 1 over the square root of 2. And we divide by this, we're going to have that in the denominator. So it's going to be 1 over the square root of 6 times this vector. So we're going to have 1 over the square root of 6. And then we're going to have minus 1 over the square root of 6. And then we're going to have 2 over the square root of 6, and then 0, 0. Now again, we could do something, we could write 2 over the square root of 6 as the square root of 2 over the square root of 3, but I'm just going to leave it like this. Okay, so that's Q2, and now finally we need to get Q3. So one thing that should be true is that these two vectors should be orthogonal to each other. And we see that that is true because we have 1 over the square root of 2 times that is exactly the negative of what we get here. So you do the dot product, those two terms would cancel out to each other, then all of these terms are equal to 0. So Q1 is orthogonal to Q2. And then if we want to compute the magnitude of this, again, if we can factor out a square root of 6, we're going to get 4, 5, 6, take the square root of that, and we see that the magnitude is 1. That's just a check to show that they are, these two vectors are orthonormal. Okay, so now let's compute Q3. So Q3 hat, we're going to start by taking V3, or let me write Q3 hat. We're going to start by taking V3, so we've got 1, 0, 0, 1, 1, and we're going to subtract off its projection onto Q1. Okay, so we're going to compute the inner product of V3 and Q1. So it's 1 over the square root of 2 plus 0 times 1 over the square root of 2, and all of the other ones are going to be zeros as well. So the inner product of V3 and Q1 is simply 1 over the square root of 2. And we're going to multiply it by 1 over the square root of 2, by Q1, 1 over the square root of 2, 0, 0, 0. Okay, then we're going to subtract off the projection of V3 onto Q2. Okay, so what's the inner product? Well, we're going to have 1 times 1 over the square root of 6, but then notice there's going to be 0 times that plus 0 times that plus 1 times 0 plus 1 times 0, so a 0 in all of the other pairs. So it's just going to be 1 over the square root of 6. 1 over the square root of 6, and then times Q2, 1 over the square root of 6, minus 1 over the square root of 6, 2 over the square root of 6, 0, 0, like this. Now, as I did in the previous one, I can when you multiply the 1 over the square root of 2 in here, these just become 1/2. And so what we're going to get is 1/2, 1/2, 0, 0, 0. Okay, and now similarly over here, when you put the 1 over the square root of 6, we're going to have 1 over 6 minus 1 over 6, 2 over 6, 0, 0. Okay. So as you can see, it's really only on this one where the arithmetic gets a little bit irritating, but I have confidence that we can do this. So 1 minus 1/2 is 1/2. 1/2 minus 1/6 is 1/3. Well, yeah, that's right. 1/2 is 3/6. So 3/6 minus 1/6 is 2/6, and that is 1/3. Then we're going to have 0 minus 1/2, but plus 1/6. Okay, so it's minus 1/2 plus 1/6. So minus 1/2 plus 1/6. So 1/2 minus 1/6. Sorry, 1/2 minus 1/6 is 1/3, but it's negative of that, so it's going to be minus 1/3. And then for the third entry, it's going to be 0 minus 2/6, so minus 1/3. And then 1 minus 0 minus 0, so we're going to have 1 here and 1 here. And as it was when we computed Q2, it'll be a little more convenient to factor out a 1/3 when we're computing the norm. Oh shoot, I just forgot. I erased it over here. R13 is 1 over the square root of 2. Let me make this how I had the other one. The square root of 3 over the square root of 2. 1 over the square root of 2, and then R23 was equal to 1 over the square root of 6. Okay, so I'm going to have a 1, a minus 1, a minus 1, and then a 3 if I factor out a third. Okay, so then what is R33 equal to? Well, it's going to be the magnitude of this vector divided by a third. Hold on, something popped up on my computer here. Let me get rid of it. Okay, so 9 plus 9, that's 18. 19, 20, 21. So 21, the square root of 21, we're going to have the square root of 21 divided by 3. So 21 is 7 times 3, so this is equal to the square root of 7 over the square root of 3. So R33 is the square root of 7 over the square root of 3. And then now what we're going to get for the Q3 is going to be this vector divided by that. In other words, multiply by the reciprocal. Okay, so what's going to happen is we're going to have the square root of 3 in the numerator divided by 3, and then the square root of 7 in the denominator. So overall it's going to be 1 over the square root of 21. Okay, so let's see. We're going to have 1 over the square root of 21. We're going to have minus 1 over the square root of 21. We're going to have minus 1 over the square root of 21. And then we're going to have 3. Sorry, I'm going to sort of write it like this now. Over the square root of 21, and we're going to have 3 over the square root of 21. And I'm not going to simplify those last two. Though maybe, I'm going to keep it all having the square root of 21. Okay, and you can sort of verify that the magnitude of this vector is going to be 9 plus 9, 18, 19, 20, 21. The square root of 21 divided by the square root of 21 is 1, so this vector has unit magnitude. And then you can also show, we already showed that Q2 and Q1 formed an orthonormal set. What I just showed shows that at least these three vectors form a normalized set, that is, they all have unit magnitude. Let's show they are also orthogonal to each other. If I do the dot product of Q1 and Q3, I'm going to have 1 over that times 1 over that, and then 1 over that times minus 1 over that. So because we have a 1 and a minus 1 and a 1 and 1 there, it's clear that the inner product of Q1 and Q3 is going to be equal to 0. And then if we notice what's going to happen for Q2 and Q3, we've got 1 times 1. Notice the denominators on all of these are the same. So we can just look at the numerators. 1 times 1 plus 1 times 1 minus 2. So 1 plus 1 minus 2 shows that Q2 and Q3 are orthogonal, and then 0 times that. And okay. All right, so it shows that this, in other words, what I just verified is that Q1, Q2, and Q3 are an orthonormal set of vectors. That means they're linearly independent. Assuming I did all of my arithmetic here, Q1 correctly, Q1, Q2, and Q3 are just linear combinations of these vectors. So they span the same space. So Q1, Q2, and Q3 are in the vector space spanned by these 3 vectors because they are just linear combinations of the columns of V. Okay, so this means that these 3 vectors, the span of these 3 vectors, are in the span of these 3 vectors. These 3 vectors are linearly independent, and there's 3 of them, so it means they form a basis for this set as well. Okay, so this again, some basic linear algebra stuff. If you have a subspace of dimension n, and you have n linearly, or so let's say you have a subspace of dimension m, as in Mike, and you have m, that is m as in Mike, linearly independent vectors in that vector space, then they form a basis for that vector space. And that's exactly what we have here. Okay, so this is just, this last example here was just to show you, because it was kind of abstract when I was writing all of this algorithm stuff here. I just wanted to show you a concrete example of computing the Gram-Schmidt orthogonalization process and also the QR factorization for a matrix. This is something that in the programming lab this week we might do. I haven't decided yet exactly what I want to do for the lab this week, whether or not I think that will be useful. It's just something that I'm going to think a little bit about before I make any decisions. But even if you don't and you know how to do programming, this would be, which I hope you do if you're taking this class, then this might be an interesting thing. Coding up this Gram-Schmidt algorithm in Python might be an interesting thing to do. Okay, all right, that's it for this video.